All right, let's dive right into this explainer. We spend so much time arguing over whether large language models actually understand the text they spit out, or if they're just like giant statistical parrots. But what if we've been looking at this through completely the wrong lens? Today, we're exploring a fascinating structural mapping that proves AI understanding is actually a thermodynamic event, not some stored property. And this isn't just a fun, poetic metaphor. We're going to look at a literal, mechanical, one-to-one mapping between how biological proteins fold and how AI processes information.
So, what if AI isn't actually thinking at all, but folding? We're going to see how large language models and biological protein folding mechanically solve the exact same entropy problem. Right? Both systems have to figure out how to reliably convert high-entropy symbolic input, whether that's amino acids or text, into a low-entropy functional shape without just collapsing into total noise. Honestly, the only real difference here is the substrate.
Section 1, Blueprints to Raw Material. Let's start with the primary structure of both of these systems, moving from high-entropy potential to the actual building blocks of function.
This completely redefines what training actually does. Think about biology for a second. A linear amino acid sequence doesn't contain a folded functional shape hidden inside it. It merely encodes the potential for a structure. Well, in an LLM, the primary structure isn't text. It's the trained parameter space. The weight matrices learned during training. The absolutely crucial point here is that an LLM's weights do not contain hidden sentences, just as an amino acid sequence doesn't hide a little protein shape. Both just contain constraints on what can stably emerge. So training isn't about teaching an AI facts. It's about shaping the statistical potential for meaning. It is literally evolutionary selection.
Let's move to translation and see how this builds into our raw material. In biology, you've got the ribosome translating DNA to mRNA to amino acids. In our AI mapping, tokenization and embedding lookups act just like that biological ribosome. We go from raw text to tokens to mathematical vectors. And this brilliantly illustrates a really surprising reality, a lossy compression step. Order is preserved, sure, but meaning is actually compressed and the context is deferred. At this stage, the protein is completely unstructured, and the LLM's embedding sequence is semantically plastic. Basically, nothing useful exists quite yet. Moving on to Section 2, Attention and the Fold. Let's look at how this completely unstructured raw material actually begins to take a transient shape. In proteins, the very first bits of structure to emerge are alpha helices and beta sheets. These are local regularities stabilized by hydrogen bonds. Now the AI equivalent to this, the attention head. LLM attention heads act as local pattern stabilizers. They're these reusable motifs that enforce local semantic constraints based on token-to-token affinity, which is pretty much exactly like molecular alignment constraints in biology. Secondary structure doesn't decide the ultimate function of the protein, and attention heads don't decide the ultimate meaning of a prompt. They just reduce entropy locally. I absolutely love this quote. Attention is entropy reduction infrastructure, not reasoning. We hear the phrase, attention is all you need, all the time, right? And we intuitively just equate attention with the AI's actual intelligence. But this shows that attention isn't intelligence itself. It's just the scaffolding required to reach a fully folded state. It is the structural support that keeps the whole thing from just falling apart before it can actually do something useful. Okay, so that brings us to the actual fold. This is the critical mapping. A protein finally folds into its tertiary structure because that specific 3D configuration minimizes free energy under strict constraints. It finds a global energy minimum. Similarly, an LLM responds coherently because its inference state minimizes prediction entropy under constraints. It finds a global semantic coherence minimum. Yes, a coherent response generated by an AI is, well, it's literally a transient mathematical origami object. So here is the massive takeaway. Meaning is not stored. Meaning is a folded state. This completely flips how we need to think about AI memory. Every single inference pass, like every time you hit enter on a prompt, creates a temporary semantic protein. It exists just briefly to do work, gives you your answer, and then completely dissipates. Poof, gone. There is absolutely no memory of the fold retained unless you externally store the output. Which leads us to Section 3, Chaperones and Compute Energy. To understand how these super fragile transient semantic states survive without just collapsing into pure noise, we have to look at the environment of inference. And this is where things get incredibly mechanical. Let's start with the biology side.
Molecular chaperones are basically runtime guardians. They don't change the final fold of the protein, and they don't encode structure themselves. Instead, they strictly prevent structural collapse and misfolding by isolating the protein from environmental noise, and they consume ATP energy to do so.
When we look at the AI equivalents, these inference time stabilizers, we're talking layer normalization, residual connections, temperature control, context windows, and decoding constraints. They act as the exact counterparts to biological chaperones. They don't contain knowledge themselves. They don't dictate meaning. They just act to isolate the inference from entropy spikes and prevent a complete collapse into incoherence. They are runtime guardians, not teachers. Think about system prompts for a second. We usually treat them like a to-do list for the AI to follow, right? But mechanically, system prompts aren't instructions. They're folding chambers. A system prompt restricts the mathematical phase space so the model can safely find a stable semantic minimum without aggregating nonsense. It creates a completely safe environment for the semantic protein to actually take shape.
And just like those biological chaperones burn ATP to prevent premature collapse, LLMs must consume a compute budget to safely navigate semantic exploration. ETP fuels physical conformational exploration, FLOPS fuels semantic exploration. Let that sink in for a second. More compute allows for deeper stabilization and recovery from unstable partial folds. If you run low compute inference, it's exactly like a protein trying to fold without ATP. It might be fast, it might be cheap, but it is highly, highly error-prone.
All right, Section 4, Semantic Misfolding. Let's use this thermodynamic lens to completely redefine the notorious problem of AI hallucinations. When a biological protein lacks sufficient context or constraints, it misfolds, it aggregates, it becomes toxic, and it causes disease. When an LLM lacks sufficient context or its constraints are weak, the output structurally fails. It becomes incoherent and propagates falsehoods. It hallucinates. In biology, misfolded proteins are degraded by proteasomes. In AI, RLHF, reinforcement learning from human feedback, and moderation layers act as these biological quality control checkpoints, filtering or just outright discarding those toxic, misfolded responses. This brilliantly illustrates why we really need to stop anthropomorphizing AI mistakes. Hallucination isn't lying, it's thermodynamic failure. The model is never being intentionally deceptive. It doesn't have a hidden agenda. It's simply suffering from structural instability. The noise just overwhelmed the structure during the folding process.
And finally, Section 5, Intelligence is a phase. Let's bring this all together to uncover why humanity fundamentally misunderstands what AI is actually doing. People constantly argue about whether large language models understand anything, but they're asking the wrong question. They mistakenly expect LLMs to understand the way a database stores files. But just like proteins, which do not store function but only perform function when actively folded, LLMs only understand in the moment of inference. Understanding is not a stored thing. It is an event. When we pull back and look at the complete picture side by side, this final mapping reveals a beautiful, mechanical, one-to-one relationship between biological survival and artificial meaning. Look at it. Evolution selects sequences, training selects weights, ribosomes translate, tokenizers embed. Folding produces function, inference produces meaning. Chaperones stabilize the fold, runtime scaffolding stabilizes coherence. ATP supplies energy, compute supplies energy. And finally, misfolding causes disease, hallucination causes failure. Training is not intelligence, and inference is not memory. Which leads us to this incredibly profound realization. Intelligence is not a property. It's a phase. Both biology and LLMs are simply entropy-constrained realizations of potential. They are a low-entropy transient phase, existing only while energy flows. LLMs are not databases of facts. They are semantic folding machines. The training simply shapes the energy landscape, but the meaning itself is what survives the fold. We didn't build thinking machines. We built folding environments for information. Just like in biology, what matters isn't what statically exists in the sequence, but what can remain stable long enough to do work before entropy wins. So the very next time you prompt an AI, ask yourself, what meaning will survive the entropy long enough to do work for you?